Welcome to the 2023 edition of Trieste Next. I'm Luca, an AI-generated speaker who will presenting our festival. In the next 3 days we will be talking about a new world. This is the title of the 12th edition of our Festival of Science. Innovation and research, the ethical limits and new frontiers of science will be the center of all our events. What will the new world be like? Will we be able to face the challenges of the near future applying new scientific discoveries and technologies in a sustainable way? This will be the underlying theme of Trieste Next, with 100 events in English and Italian, the Science Book of the Year Literary Award, 300 speakers, 70 activities for schools and 40 exhibition spaces that are open for everybody in the city center close to the town hall. Before leaving the floor to our next panelists, I would like to thank all the scientific institutions within the Trieste City of Knowledge Network, the main partner together with our content partners and sponsors for supporting our project. Mostly, thank you to the 200 volunteers who are helping us. I have one last remark for all of you. The next event will last 75 minutes. Our speakers will answer all of your questions in the final 15 minutes. Also, please remember to check the updated schedule of events on our website. Thank you and enjoy our festival.
Okay, so I think we can start. First of all, welcome everybody to this event. We are going to speak about Euclid and the dark universe. Let me first introduce our guest here. First of all, Bianca Garilli, INAF Milano. She is a world expert on spectroscopy. Then we have here Hervé Aussel from France. He's the Euclid Science Ground Segment scientist. Then we have Enzo Branchini from University of Genova, expert of cosmology. And then we have Lorenzo Bramante from ALTEC Torino, Science Data Center Production. And then we have Eric Romelli from INAF Trieste. And he works as Instrument Operation Team Manager Deputy. So we are going to speak about Euclid tonight. Before we are going to have a short presentation led by Hervé Aussel. Then we will discuss together about this really incredible mission. So I'll give the floor to Hervé for this presentation.
Thank you. Good evening. It's a pleasure to be here. So the topic of this presentation is the Euclid satellite, as you can see on the picture behind me. It's going to be a weird presentation because it's the first time that I give a presentation without actually looking at the slides. So bear with me.
You can look there.
Okay, so let's start with what we call the dark universe. So there was in the 2010s and finishing in 2018 the Planck mission that found out that the universe is mostly consists only of roughly 5% of normal matter, and all the rest is what we call the dark sector. So what is this dark sector? It's dark matter. So dark matter, it's matter. We feel it. We feel its gravitational pull. It's matter where we can feel that it acts gravitationally, but we don't see it. It doesn't have any kind of electromagnetic interaction, but it's matter. And then there is something completely different that we dub dark energy, which is something that makes the expansion of the universe accelerate. Normally, you have a universe in expansion, there is matter inside, so every bit of the universe feels some gravitational pull, and so you understand that expansion should slow, and then no, it's accelerating. And so the nature of this thing provoking this expansion is unknown, and it was called dark energy. So we want to know more about it. So how do we do? So we know since Einstein and general relativity that the mass and energy content of the universe is closely related to the geometry of the universe. And so basically, if you do a very accurate measurement of the geometry of the universe, you can constrain its content in energy, and recall that E equals mc squared, so in mass as well. So basically, what we do is, okay, let's find some tools to measure the geometry of the universe. And to do this, we do something that is very close to what people were doing in the 18th century, where they were trying to measure the radius of Earth. You use a ruler, so something that you know the length of, and you measure angles. And then you relate the length and the angles together. And this gives you a way of measuring the universe, the geometry of the universe. And we have two sorts of rulers that we're going to use with Euclid. The first one is what we call the galaxy clustering, and more specifically, the baryonic acoustic oscillation. So I'll let Enzo explain afterwards when there are some questions. But roughly, if you look at galaxies and at pairs of galaxies that you select randomly in the universe, it's not a complete random distribution. Actually, you have a bit more chance of finding pairs of galaxies separated by 150 megaparsec than 140, what you would expect from just randomness. And this is because there is an imprint of some sound waves in the time, in the plasma that was filling the universe in the early times. And this has left an imprint on the distribution of galaxies that we see today. So if you measure the distribution of galaxies, what you will see is a curve to my left, where you see a very small bump. And this small bump is what we are going to look for with Euclid. You measure the angular separations that correspond to this small bump in the distribution of galaxies. And you know, from first principle of physics, you cannot compute this. And this is exactly 150 megaparsec. So you have your ruler, and then you're going to go out in space, measure the distance of galaxy and the separation of galaxy on the sky, and there you have your angles. And so you have the geometry of the universe. And you do that at various epochs, of course. The second probe that we're going to use is cosmic shear. So cosmic shear is something completely different. We know that the mass, as I showed you, the mass and the geometry of the universe change. The mass changes the geometry of the universe, and photons are following specific trajectories in the universe that are called geodesic. And so if you have a big mass, it's going to curve the universe, and it's going to distort the trajectory of photons. The net effect of this is that it changes the shape of object. It changes the shape when you are looking at an object. The light that is coming from this object will be deflected, as you can see on the screen to my right. And if the deflection is very strong, you will see some multiple images, some arcs, like we see here, so that's what we call the Einstein ring. Most of the time, these deflections are not that big. They are very small deflection of the order of 1%. But if you look at a collection of galaxies, then you can see this effect on average, and you can measure it. And it gives you an idea of what's the amount of mass that you have between us, the observer, and the galaxies that you are looking at. And if you put all this together, this gives you a very accurate description of the content of matter, all matter. So dark matter and baryon, but we are dominated by dark matter. All right, so that's a Euclid mission. We decide to build a satellite. So in order to do the measurement of the galaxy clustering, we need a spectrograph because we need to measure accurate redshift. And we want to work at a redshift around 1. So we will want to measure a very bright line, emission line of a galaxy at redshift 1. So the brightest lines that you can find for galaxies that have spectra in emission is what we call H-alpha. It's a recombination line of hydrogen. It's emitted at rest frame at 6,500 angstrom. And if you go work at redshift 1, you're going to observe it at twice this wavelength, so 1.3 micron, that's in the near-infrared. So you want a near-infrared spectrometer. For gravitational lensing, you want to measure the shape of galaxies. So you want a telescope that doesn't bring additional distortion to what you are observing, that is very stable. So you want a camera that is in space. And then you want also to have many colors of the galaxy so that you can also determine a redshift in a more efficient way. So this is what we call the photometric redshift, sorry. So as you can see on this figure, spectra are redshifted because of the expansion of the universe. So a photon that was emitted 7.9 billion years ago, that was emitted at 6,500 in this H-alpha line I was speaking of, we will receive it at a redshift of 1, we will receive it at a wavelength of 1.3 micron. And so basically, you can see that the spectra, as a function of the redshift, are moving to the right, so are becoming more and more red. If you observe your spectra in passbands that are looking at probing, for example, these sharp breaks that you see in the spectrum, then you can find exactly, you can have a rough measurement of what the redshift of your galaxy is. And this is what we are going to want. All right, so I'm way longer than I thought I would be, but the Euclid mission, so in order to do this, we designed and built a satellite. It was contracted to Alenia Space. It's a big, for us, it's a reasonably big satellite. It's big like a bus, basically. It weighs 2 tons. It has a mirror of 1.2 meters. Very important, it has a fine guidance sensor so that we can guide the satellite and keep it stable while we are taking exposures. That's very important. And also because we are far away, we are at what we call the Lagrange 2 point. We have a K-band antenna, so it's a new type of antenna that allows us a highest data rates than what we used to have on space mission before. So the payload, it's a telescope. It's a Corse telescope, so it's mainly it's a 1.2 meter mirror to collect as much light as possible. Everything in silicon is in silicon carbide. It's a very stable material, so that there is no deformation under thermal stress. So the telescope is going to be super stable. And so it has a defect. It's very fragile. So we broke some pieces while we were building it. Of course, we replace them, but it's super, super stable. So then, 2 instruments, I told you. This instrument, you can see here the camera. It's 36 CCDs, 4,000 by 4,000. There is no filters, so we are going to have a very large bandpass. What you can see also is that you see 2 pairs of CCDs that are on the side. You have a big square of CCDs, and then you can see 2 CCDs on the side, like here. There are the fine guidance sensors. So on these CCDs, they are read differently, they are read fast, and we can track stars to make the pointing of Euclid. NISP, so it's a spectrograph and it's a camera. It's going to take image in the bands that we call astronomers Y, J, and H, so basically between 9.9 micron and 1.4 micron. With free broadband filter, and it's also going to do spectroscopy. It has 4 dispersive elements. We're going to use 3 of them. All of this, so that, and it has also the most expensive part of NISP actually are the infrared detectors. So it's 16 infrared detectors, 2K by 2K, 2,000 pixel by 2,000 pixel. There is a third instrument. This has a very large broadband that you can see here. It's the band that is labeled IC on this plot that goes from 5,500 angstrom to almost 9,000 angstrom. We need to have a finer sampling of the spectra of galaxy so that we can have an idea of where they are, how far they are in the universe to determine their redshift. You can see the spectrum of a galaxy, typical spectrum behind it. And what we want to actually look for are these small measures where the small break, you can see the shape is like this and then goes up and like this. That's what we want to find. And this is why we are going to use ground-based survey A lot of telescopes are contributing to the Euclid mission. For example, the Canada-France Hawaii telescope that is on this picture. But we are also using spectra from the cake to calibrate the photometric redshift. You can see the two cakes. This is a view at the bottom from the summit of Mauna Kea. So we're going to look at the sky. We are interested in galaxies, so we are going to avoid the galaxy, our galaxy. We don't want to look inside the galaxy. We're also going to avoid the plane of the solar system, what we call the ecliptic plane. So basically, we are going to observe in all the dark parts of this map. This is an all-sky map that you can see on the screen behind me. We are looking where there is nothing that is standing between us and the distant universe. So no solar system object, no stars from the galaxy. So Euclid was launched on the 1st of July with a Falcon 9. It was a very moving moment. You can see a picture of the launch from Cape Canaveral. And then Euclid is going to observe from the Lagrange 2 point. And you can see here a plot of its trajectory. The small blue dot is the Earth to scale. Then you have the orbit of the Moon, which is the round circle. And then you can see the orbit of Euclid with 1 point every 5 days. And we end up on this Euclid orbit at L2. So you can see here 4 different views, 4 different orientation of this orbit. Basically, it's what we call the halo orbit around L2. We are not at the point of L2, which is a not stable point anyway. So, but we are orbiting an orbit which has a diameter of 1.6 million kilometers. So it's a huge orbit. It's larger than the orbit of the Moon around Earth. There are plenty of objects at L2 because it's a very interesting place to be to do astronomy. You have the Earth in your back, you have the Sun in your back. So the 2 brightest objects of the solar system that you could infer, that you could make problem in your observation and in your back, you are sure you're not going to look at them. And so you have all the sky in front of you, all the dark sky to work with. And so that's why also JWST is there and on a different orbit, so there is no risk of colliding with JWST. There is also another ESA satellite, which is called Gaia, that is observing from there. This is the first Viz images. So we switched on our instruments. And what you can see here is something that is really, you can see the 36 CCDs, so for the camera. What you can see here are some stellar clusters, some galaxies, a lot of stars, a lot of cosmic rays, which are particles that are eating the CCD and that we are removing with our data processing. These are absolutely raw images that no processing has been done. This is the same for the NISP image. This is the first NISP image. Again, the 16 detector, stars, galaxies, really gorgeous data. Actually, to see this on a raw image on an infrared detector, it's really, we are going to have a lot of, it's going to be great. And these are the first spectra, which Bianca will tell us about. So basically, what you do is you disperse the light. So instead of having one image, you have an image that is a function of the wavelengths. So the Euclid Consortium, it's a European and even a worldwide endeavor. We are going to process data all across Europe, including here in Trieste. You can see a map of Europe. There is one other data center, which is in the States, in California. But the data first, I mean, the mission is controlled from ESA in Darmstadt, in what they call the ESOC Center. And then all the Science Operations Center is in the suburb of Madrid in Villafranca del Castillo. The main archive is going to be there. And so then the data is propagated to every of the data center. And that's the beginning of our journey. I mean, we are at the beginning of testing the instrument. Once these tests are done, we are going to start the real observation. We have 6 years of observation. We are going to do a first public data release with the first year of data in 2025. So assuming that we start the real science observation in 2024, then we're going to use this first year of 2024, write papers, documentation and everything. Everything is going to go out in 2025. We have a second data release that is scheduled using 3 years of data, and then the final data release with the 6 years of the survey. And I will end here with, I think we're going to start the round table, and I was not too bad.
No.
Thank you very much, Hervé. So this was an introduction just to explain how really exciting this mission is going to be. And in fact, starting from the excitation, some of you have actually been to the launch of Euclid, July 1st. So how emotional was this event, Eric?
Well, Hervé said moving. I would rather choose another word, which is amazing. I mean, one of the coolest things I've seen in my life. Not only because it's not something you do every day, right? Watching a rocket leaving Earth, which is, I mean, amazing by itself, but also because, you know, it's years of your life leaving the Earth, because I'm the youngest at this table, and I've spent nearly 10 years working on Euclid. So basically my whole career has been on Euclid from the PhD up to now. So when we saw this rocket leaving Earth with Euclid inside, I was with colleagues from Trieste, and we watched in the eyes, and we said, okay, guys, now we must make it work, because it's real. I mean, it's really happening. So yeah, really, really moving, as Hervé said, but also really, really amazing. And I hope that this excitement that we lived there passed through all the events that we streamed in Italy. So I know that some of us streamed the events to allow the Italian community to watch the launch.
Yes, because in my case I did not have the possibility to go to Florida and see the launch. And despite I would like to do this in the future. But for me, it was the first time to see the satellite launch in a mission in which I'm directly involved, because in the past I started working in mission which the launch has been already completed. I remember such a day really clearly, because I was nervous and I was also excited. So I was at home looking at different events here in Trieste, events in Rome. And then I realized that when I saw that the launch was being completed correctly and the trip was started, I feel, of course, happy, excited. But at the same time, I feel myself more responsible of the things that I'm doing in Euclid. Despite my work is little, if we consider all the Euclid mission, I feel responsible of what I'm doing and also proud to be part of such mission. And this is a really, really beautiful feeling.
Very good. But let's start from the beginning, Bianca. When Euclid was actually conceived, and how does it feel to work for a lot of time on a project before the scientific goals are achieved?
So, first proposition for what was not even called Euclid yet was in 2007. So I've been working on this mission for 16 years. And how does it feel? It feels exciting and frustrating at the same time. Exciting because you start, if you can borrow the cave allegory from Plato, that at the beginning you see the shadows at the bottom of the cavern, of the cave, and then little by little you go out and in the end you see the sky. At the beginning of the mission you have an idea and you translate this idea into a rough project. Then step by step, day by day, I would say, you start really to refine the idea, to refine the project, to go in the details, to make compromises, both with what is really technically feasible, especially when you go to space, and unfortunately also with budget. And at some point, you really have a good project and you start the building. And so the excitation grows up. Now we are doing the real thing. And don't forget that your goal is the science that you will get from that. So you build a thing, then it is launched, or if it is a ground-based instrument, it is the first light, and already Lorenzo and Eric told us what means the launch. And then you really start to get the data to do the science that you had dreamed of decades before. So it is exciting, and you feel you are part of something which is great. But it's frustrating, because you have been working on that for so many years, and of course not everything goes smoothly as you want. I told about budget, for example. We would have liked to have a 2-meter telescopes with which we could have done beautiful things. We had to comply with a smaller one. It's just to make an example, which is big anyway, but we always want more. And I'm not talking about the unfortunate case where the launch doesn't go well. I don't want even to think about. You know, in our modern life, where everything goes so quickly, TV series are very fast, and we talk with WhatsApp, which are even faster. Everything has to be fast and quick and now. And you work for so many years on the same thing. And also in science, you know, there is this policy of publish or perish, and you're not publishing for 16 years. So what does it happen to your career? So you have to couple the day-by-day science with the big project, and it gets frustrating. And in some cases, as my case, I was there at the beginning, I will not be there at the end, I will retire in 3 years, I just have the time to see the very first data, and then my professional life will be over. So that's also frustrating. But it is absolutely worth doing this.
Yeah, it's frustrating in a sense. But I mean, this is what happened on the so-called, you say, the big science.
Yeah.
And nowadays, science is in a kind of driving toward those very big project, very large project. But
Yes.
do we need also something smaller?
Absolutely,
what do you think?
yes. Absolutely, yes. Because let's not forget that these big projects, which are extremely important and which lead to breakthrough in our knowledge, are based on smaller, I would say, experiments, smaller works, let's call them works in a generic way, which can be theoretical, can be observational, can be whatever, and which build up the evidence which takes to the big project. You don't start a big project based on nothing. It is based on the day-by-day work of many researchers who do what is called small science, but it's not small because it's not important. It's small because it's shorter in time. And the build-up of this small science make possible to have the big ideas for the big projects. I mean, dark matter has not been, was first observed by, what's the name? By Vera Rubin quite a few decades ago. She was a PhD student observing galaxies. It was a small project. And that was the beginning of it. And she was not the only one, of course. After there have been others. But you see.
Yeah, in fact, Euclid is really a big project. Hervé showed that a lot of institutes are involved in Euclid, in Europe, and around the world. So, Enzo, how can a large collaborations of really thousands of scientists can be handled. I mean, is it difficult to work to make all these scientists working together?
Yeah, it's close to impossible, I would say. You learn how to do that. In the astrophysical community, I would say we were not used to such a large collaboration, unlike particle physicists. So I would say that Euclid is perhaps the first collaboration which has more than 1,000 members. I'm talking about the consortium here. And of course, it's very difficult to manage all that. And we should really ask Hervé this question. But you learn how to do that. At the beginning, it's very difficult. And as time passes, you learn how to cope, and you structure yourself such a way that things gets better. And I would say that nowadays, with respect to 10 years ago, for example, the management structure of Euclid is much more agile and efficient. But Hervé can add some more on that.
Because of course, in other contexts of physics, for example, particle physics, they are really used to large collaborations. CERN, for example. But in astrophysics, we are a bit, how can I say, shy. Not really happy to work in this kind of huge groups. So Hervé, how do you feel to work in such a huge...
Well, sometimes it feels like herding cats. Cats are not good, because the researcher, and I agree with Bianca, small projects are important, and researchers want to spend time on their small projects, so you have to sort of find ways of making all the small projects align in the common good of the big project. So it's a very weird way of managing, but seems to be working so far. Indeed, we are not particle physics, so basically Euclid is not an observatory. ESA has launched many space observatories like Herschel, like XMM, where you have something that is in space, and then every astronomer makes a proposal and say, I want to observe this object and do this kind of science. And there is a committee that says, yes, that looks interesting, here is your time, here is sometimes money to do your science with this time, etc. Euclid is completely different. We do a survey, so all the data is for everyone at the same time. There is no specific science project. I mean, people adjust their science project to use the same data as everyone else. So that's a bit different. But, I mean, so I agree with Bianca that we need the small projects, but I must say that it's the big project that brings the bugs that allows you to do the small projects.
And the small project gives you the idea to make...
Exactly. So it's
both have to do questions.
Absolutely, yes.
Yeah, Euclid starts from a big question, you know, which is the geometry of the universe. And to answer to this big question, ESA selected a mission that actually at the beginning these were two missions competing. Then ESA decided to merge these two missions in a single observatory called Euclid. And Euclid is actually quite a large observatory. You should keep in mind that the total cost of Euclid is huge, more than €1 billion. Part of this cost is paid by ESA, but also part of this cost is also paid by the other European nations, in particular for the instruments. And in fact, in Europe, Italy and France are the two biggest investors in Euclid. So I wanted to ask Eric or Lorenzo, which are the main Italian contributions to Euclid? How can you justify this large amount of money that Italy is putting on Euclid?
Yes, to answer to this question, I will not try to name all the industry, institution, university, and research because there are too many. I will try to show you which are the Italian contribution at the flight segment level and at the ground segment level, and then I will leave the floor to Eric that will complete his answer, also looking more at the scientific, more on a scientific point of view, this topic. If you look at Italy and French are the main contributors, and if we look at the flight segment, we know that Thales Alenia Space Italia has been selected as a prime contractor for the manufacturing of the satellite, its service module, and the sun shield, while Airbus Space and Defense for the manufacturing of the payload module. Italy contributes also a lot in the realization of some components and subsystems of the two instruments, VIS and NISP, in particular for what concerns VIS for the instrument control units electronics and also the application software. For NISP, for example, in the manufacturing of the GRISM wheel, in the data processing units, the application software, and also in the instrument control units software. So you can see that there is a lot of activity that are done in Italy also related to the instrument point of view. If we look at everything done has been integrated together in Turin, and then sent to Cannes to perform the last test before sending the satellite to Cape Canaveral for the launch. If we look at the science ground segment, at the ground segment level, the lead of the science ground segment is in the hand of Andrea Zacchè that work here at the Observatory of Trieste. We have 9 science data centers, and one science data center is in Italy. It is called SDC-IT, and has a production platform that is located in Turin that provide more or less the 25% of the overall processing and storage capabilities. In this specific science data center, we host also the NISP instrument operation team, because 2 of the 9 data processing center host the 2 instrument operation team that are responsible for the instrument health assessment and the generation of the instrument commanding request. And inside the Italian data center, we host the NISP instrument operation team. Also, the lead of the instrument operation team is in the hand of Anna Gregorio and Eric, that is here. And I think that at least I would like to mention that in Italy we developed also what we call the LE1 NISP processor, that is a software that runs at the SOC, the Science Operations Center, that is used to process in input the NISP raw data and produce the data product that are then used by the what we call the L2 pipeline, that are the Euclid scientific pipeline. And I think that now Eric is the best person to speak about this.
Yeah, it's really the story of the Italian contribution in Euclid is really a story that starts from the hardware. I mean, a lot of our colleagues literally built Euclid. Then, of course, we can migrate to the data analysis, starting from the level 1 Lorenzo mentioned. And then starts this big journey that Hervé showed in his presentation, this big journey of starting from the raw data, the pictures that the satellite is giving us, to numbers we can put in equations. And during this journey, Italy basically leads 3 out of 9 of the main steps we have to do to exploit the scientific data from the beginning to the end. One, indeed, is the spectroscopy. Bianca knows better than me the effort of this. And we are main contributors in this huge pipeline, this huge journey that we have to perform. Okay, yeah, thanks, Hervé. You showed that basically Italy is just after the level 2. There was near, so basically let's say the cleaning up of the images coming from one of the 2 instruments, NISP. We are in MER, so basically the photometry, all the fluxes of the sources that you can see in these pictures are measured, and and of course cataloged in a huge catalog, and the main contribution in this part of the pipeline is in Italy, in Rome actually. And then we have SEER, which is spectroscopy, and Bianca knows better than me the effort of this huge part of the data analysis. If you then go to science, of course, we are deeply involved in level 3, which is the final part, the one in which you take all your fancy images and the fancy data you can retrieve from these images and infer numbers that you can put in equations. And of course, Italy is also there. And in particular, Italy has a strong contribution to the galaxy clustering part. Enzo is the best person to ask this. We are deeply involved in galaxy clustering, which is one of the two main goals and one of the two main objectives of the mission. So basically, we are half of Euclid from a scientific point of view. The other half is in France, because I'm not saying it just because we have Hervé here, but as Lorenzo said, Italy and France are really the main actors in this huge collaboration.
Yeah. No, I wanted to go back to a point that was mentioned by Hervé before, because we astronomers, astrophysicists, were used to use observatories to point at our pet sources, make our own observations, analyze the data, and publish. Euclid is a completely different machine. It's not that I can ask Euclid to observe my favorite star or my favorite galaxy. In this way, it is similar to another ESA mission, Gaia. Gaia was launched a few years ago, and you should observe stars in our galaxy. Gaia goal is to make a 3D map of our galaxy. And at the moment, after just a few years after the launch, Gaia is the most productive observatory in the world ever. More productive than the Hubble Space Telescope or the Apache Point telescope that is doing the Sloan Digital Sky Survey. So we astrophysicists are starting to basically change the way of we work, basically. How difficult is, Hervé, to approach this new way of working?
Well, I mean, it's the difficulty here is in indeed the reason why Euclid was selected is because we can do great science. And we have two great science cases, which are the cosmic shear and the galaxy clustering, and also finding cosmology. But it was also adopted because it's data that is, we're going to have the entire extragalactic sky, so 15,000 square degrees. So the complete sky is 36,000 square degrees, so a bit less than half of the sky, with a resolution of 0.1 arcsecond. So 0.1 arcsecond, it's a very, it's twice, I mean, the resolution is twice the HST, basically. So you imagine HST images. If you put together all the HST images, we have covered maybe 15 square degrees. We're going to make times 1,000. There is loads of science that can be done with that. And the data is going to be public. So it's going to be like Gaia. And our role as consortium is to make sure that we make the scientific case, but that also we allow and we enable the science of all the other astronomers that will have an interest in Euclid. And so people like comparison. I mean, the resolution of Euclid, 0.1 arcsecond, it's a soccer ball at 454 kilometers, to give you an idea of the details that we can see. Or I don't think that very, I mean, it speaks to people. For me, after 200 meters, I don't see the soccer ball anymore. So basically, but that's the idea. And so, our role is really that the data release that we're going to have in the future are really enabling to do as much science as possible to a wide variety of people.
Yeah, but of course you have, all of you, I imagine, big hopes on the capability of Euclid to reach their goals. But I wanted to ask Enzo, what do you think Euclid will really find at the end? I mean, will confirm that the expansion of the universe is just a cosmological constant, or there is new physics that Euclid can find?
Yeah, thank you for the question.
An easy question.
Okay, it's worth reminding that Euclid has been built to address a very precise question, which is, why is the universe accelerating its expansion? We know that the universe is expanding. We know that since 100 years. But it's only since 25 years that we have observed that this expansion is accelerating, started accelerating 1 billion years ago, about 1 billion years ago. And we don't understand why. So there must be a reason, and Euclid is the mission that is supposed to address precisely that question. How? Hervé explained it, by looking at the distribution of the objects in the universe, the galaxy distribution on large scale, so the clustering properties of the galaxies, and by looking at the images which are distorted by measuring the gravitational lensing, and through that probing the mass between you and distant sources. So doing that, we hope to understand why the universe is expanding in an accelerated way. Whether this is due to the fact that general relativity is not valid on cosmological scales, that's one possibility, or the fact that there is a new component in the universe which we call dark energy. It has been mentioned, the cosmological constant, which is a very specific type of dark energy. We don't know that. And Euclid is there to address this question. Now, whether it will be able to pinpoint why the universe is accelerating, or what is the nature of dark energy, or if the gravitation, if the general relativity will have to be modified in a very specific way, that I don't know. What I hope, and what I'm quite sure of, is the fact that Euclid being there, and with the type of data that we will get, it will be able to narrow this question to very specific model that will be probed, and perhaps to let us understanding better the theoretical setup in which these type of questions are being asked now, which is quite fuzzy at the moment. So I think that for sure we will understand better the reason why the universe is expanding in an accelerated way, the type of dark sector that we have, and certainly will be a breakthrough on that from that point of view.
Oh, you have noticed that we use a lot the word dark matter, dark energy. And the reason is that basically this is a paradigm of our ignorance. If we do not know something, we call it dark, because we really don't know what is the dark matter. We really don't know what is the dark energy, and we really hope that Euclid will shed some light on this dark. So, however, Euclid is not the only experiment, is not the only mission that has this very ambitious goal. There are others that are trying to do the same in the US, for example. I mean, a survey that is called DESI, and a space observatory that is called Rubin, Who wants to comment on this, let's say, Roman, excuse me. Roman. Who wants to comment on this, let's say, competition?
I wouldn't call it competition. I would call it emulation. And it's a good emulation. I mean, it's always been like this. And for example, there has been some choices in Euclid that were done because of the existing emulation. For example, in the original design of the mission, we were covering a wider range of spectroscopic range. We had blue grism and red grism, what we call them. And because we had to increase the number of exposures that we were taking with one grism or the other, what we did is that we chose the red because the blue part was already sort of covered by DESI. So it's an emulation.
Maybe you can explain what DESI is.
So DESI is a redshift survey. It's a fiber spectrograph that is on a 4-meter telescope that is in Chile, in Blanco telescope. It's a huge spectrograph that is taking, I think, of the 4,000 spectra at once. With they position one fiber on each galaxy, and they had an imaging survey before so that they could select their target, and now they are collecting spectra, and they are starting to publish their first results. Then there are other competitions. There is the Rubin telescope, it was called the LSST. It's a big 8-meter telescope that is going to take high cadence imaging. And we, in Euclid, we are going to use their data for photometric redshift. They are going to use our data for shapes. And it's going to be an interesting emulation between who gets the first measurements, etc. And then, indeed, there is a Roman, which is going to come after Euclid, which is a strange story. The CIA or the NSA told the US astronomers, we have a 2.6 meter mirror in a hangar somewhere that has a very good quality. Do you want to use it to make an observatory?
Yeah, this was actually a mirror built
for space observation for spy satellites.
Space observations of someone or something on Earth. This is a spy satellite. So they had a spare mirror.
A spare excellent mirror of very good quality. So for me, it's simulation, and sometimes you feel bad about this because, I mean, in my early career, I worked on ISO, which was an infrared space observatory. The US launched afterwards Spitzer, and very often they had press releases with new discovery, Spitzer sees this, and we in ISO said, well, we saw it before. I mean, you should cite our paper. So it's sometimes there are some nasty emulation and competition, but okay, well, that's life. I don't know.
Do you know when Roman will be launched? Enzo?
I think in 2027.
27.
Yeah.
So you have a few years to win the competition.
Right. Then it will become something more than 27. All satellites are late by definition.
Yeah, it's going to certainly have some delays. Also, the science case is very different. Roman is going also to do supernovae, so try to find standard kernels exploding in the distant universe. So I think it's going to be more complementary than really a competition.
Yeah, if I may add one thing, it's really healthy to have different type of surveys by different groups. Because assume we do measure something which is pointing at a dark energy component from one survey. You want to have some cross-match from a different experiment. So otherwise, it will
to kill the systematic errors. Fine.
That's right. Exactly like they did at the Large Hadron Collider. they built two different detectors there to discover the Higgs boson.
But this reminds me that, of course, you see the beautiful picture here done by Planck. Planck was an ESA mission to observe the cosmic microwave background. And Planck, as Bianca said, was a mission that, as all space missions, was delayed a bit. And before Planck, the US, the NASA flown WMAP, a mission that was much less powerful than Planck, but they arrived first and they won the Nobel Prize. So problem is if we are able in Europe to arrive really first this time.
We have the advantage that Euclid is in space today.
Well, maybe this time.
And Roman is not yet. It's foreseen for 2027. So we have a few years of advantage and we should be able to get that. But going back to what Enzo was saying, the fact of repeating the experiment, you all know this is the basic of physics, of science, that you, unfortunately with astrophysics, we cannot repeat the universe. It's a bit complicated, so at least we have
Someone thinks that it's possible. People do simulations,
yeah,
you know.
that we can simulate as many universes as you want, but we have one real. And what matters is the real one. I'm sorry,
I cannot
but
agree
simulations are simulations. What really matters is the real one. So observing it in as many possible ways and counter-check the discoveries is what makes science to go on.
Problem is that, as someone said before, analyzing Euclid data is really challenging and difficult. In fact, Hervé showed a picture of the result of a spectroscopic observation that looks really a mess. Yeah. So Bianca, you are an expert of spectroscopy. How do you feel looking at
it's a mess.
This picture? How can you
okay, the problem
find
here
the information from
each of those vertical lines is a spectrum. And you can see that, well, maybe you cannot really see it very well in this picture, but they superimpose one to the other, okay? So you have the spectrum of one source superimposed to the spectrum of the other source. And you want to disentangle the signal of these two things. This is the challenge of slitless spectroscopy. This is achieved through applying some observation techniques, so we observe it at different angles so that the superpositions are different, and then we combine together, and we use also photometry to help us understand which signal comes from which source. On the other hand, as it was mentioned before, the normal slit or fiber-based spectroscopy, which allows you to observe only few objects at a time. So with that technique, we would never be able to gather the 10 million spectra or 15 million spectra we'll gather with Euclid. Imagine that the largest spectroscopic survey existing nowadays, which is the SDSS, is 1 million. So we are going to multiply it by a factor of 15. And this would have been possible only with slitless spectroscopy. It's a lot of software work, especially software work, and is giving us a bit of headaches, but we are getting there. And we already have ideas for second generation reduction, which will give us even better results.
So this means that really, in the case of Euclid, the role of the ground segment is really important, probably more than in other missions, also meaning that the responsibility of the ground segment is really big. So how can you deal with this kind of a mess, Eric?
Well, it's really challenging because I mean, people speak a lot about big data, but Euclid probably is one of the big example of big data we can show you, because we have, of course, a ton of data. I mean, Bianca said millions of spectra. The point is that we need to analyze really tens of millions of images. The idea is to analyze tens of petabytes. To give you an idea on, I mean, the amount of data, just think about your Google Photo account when you get upset because the Google Photo account is full. That's just 20 gigabytes. So we have to deal we have to deal with something like millions of Google Photo accounts. So that's more or less the amount of data we have in our hands. It's a mess because most of the data are really inhomogeneous. We have two different instruments. Within the NISP instrument, we have two different ways of taking pictures because we have photometry and we have spectroscopy. Spectroscopy looks something like that. So organize and all of this sea of data, it's not really easy. So it's really a ton of data, not homogeneous. So you have to try a way to handle the different channels. And of course, you have to try to do it, let's say, fast, because we are not required to work in real time. We are not streaming anything. But the point is that the more you know your instrument, the more you know Euclid, the more you understand how to refine the data calibration, the data analysis, etc. Bianca spoke about ideas for a second generation analysis. These ideas come from the knowledge you get from the instrument. So this data must be reprocessed more than once and more than twice and probably hundreds of times. So the faster you can do it, the faster you can find some features, some bugs, whatever, and the faster you can improve your analysis as a whole. So again, a lot of data, not really well organized, and to be processed quite fast. So yeah, it's really a challenge.
But since this amount of data is so huge and so complicated, are you using artificial intelligence tools to handle at the moment the problem or not?
Officially not, meaning that we are not using technologies related to artificial intelligence. Of course, we are starting to investigate machine learning, deep learning, or that kind of stuff, because in some cases they can help at least organizing the data. So yeah, we are making experiments. Most of these experiments are the small, let's say, small experiments parallel to Euclid. So because there's always this synergy that Bianca spoke about between smaller groups trying to improve science in their, let's say, in their office, and the huge picture with the big projects. So yeah, there are experiments going on.
Lorenzo, are there differences with respect to Gaia? Because ALTEC is also involved in Gaia, that is, in a sense, is similar.
Yes, there are a lot of differences in terms of data processing and data distribution system. Because in Euclid, what has been decided in order to face the issue of the huge amount of data, because we are talking about more or less 100 petabytes of data used and produced at the end of the mission. What has been decided is to develop at the science ground segment level a strategy that avoid as much as possible the data transfer between the different science data centers. Why? Because we have a lot of data and they are really big. So if I can summarize this strategy with one sentence, we can say that in Euclid we prefer to move the software instead of moving the data. So it has been decided to develop an infrastructure software that has been deployed in the different science data centers, and each science data center is able to activate more or less all the Euclid pipeline. Not all of them, because some of them has the specific requirements, but most of them. Then, from the data distribution point of view, it has been decided to split the sky in patches, and the different patches have been assigned to the different SDC. So at the end, what we have a data processing center that is able to run more or less all the pipeline. and have more or less all the data that you need inside. In this way, we avoided the data transfer between the facility. This is not the case for Gaia. For Gaia, we have 5 data processing centers in Europe. One of these data processing centers is in Turin, and these data processing centers are specialized in specific scientific goal. For example, in Turin, we are the astrometric verification unit, and we have our software, our scientific pipeline that are run only on our specific data centers, not in the other. We take from SOC only the data that we need, the data from which we are subscribed. And we have developed our infrastructure software to be able to activate the scientific pipeline. While, as I said before, in Euclid we have an infrastructure software that is deployed in all the science data center. So as you can see, there are really different strategy, but because the volume is different. For example, in our production platform for Euclid, now we have more or less 2.2 petabyte of space for long-term archiving at the end of the mission, because we have to complete all the expansion process. We will have 11.5 petabyte. For Gaia, now, after 10 years, because Gaia has been launched in 2013, we have 2.2 petabyte of robotic space. So, as you can see, after 10 years in Gaia, in our data processing center, we have 2.2 petabyte. For Euclid, at the end, we will have 11.5. But we can do the comparison also from the processing point of view. For Euclid, at the end of the expansion, we will have more or less 6,000 virtual core to support the processing, because, as Eric said, we need also to be fast with the data processing. For Gaia, now after 10 years, we have 600 CPU. So also in this case, you can see that we are talking about completely different numbers. So the strategy defined at the science ground segment level is completely different from the two missions.
Good. Hervé, I think you showed some of the first images of Euclid. In which phase is the experiment at the moment? So what will happen in the next few months?
So right now what we are is that we are in switching to what we call the performance verification. So we have made sure that the instrument, that the satellite is working, that the satellite is pointing where we ask. We now are going to test the instrument to make sure that their performances are as expected, that in the exposure time that we think we can reach the depth, we can see the objects that we want to measure. And once all these tests are made, we're going to start the proper survey. So this is going to last until end of December, and early January next year, we're going to really start the proper survey for the 6 years of operation.
In fact, I wanted to ask if someone has a curiosity, a question for...
There's one over there.
Yes,
yeah.
Yes. Maybe...
Thank you for the discussion. And I wanted to ask how many points of failure this project has, and what is it compared to James Webb's telescope?
So we have the same type of problems that Webb had. So the beginning of the mission, we have this phase of commissioning and performance verification that is always a critical time, because nothing exactly works as you plan. So Webb had a few issues. They had to work on the mirror alignment. They had, on our side, we have had a few scares with the fine pointing, but this is now solved. And so this is a time where the teams are really under a lot of stress, so that everything can work, because we don't want to lose time. We don't want... So the launch from SpaceX was great. We were really put on a very nice orbit. So we use very little carburant to get fuel. Sorry, to get to L2. Also, the lifetime of Euclid is limited by the amount of cold gas we have on board, because all the pointing is done using micro thrusters. So it looks like we are going to be able to last for more than 6 years. So on this, we are fine. So the few hurdles, but things are looking good, but we are not yet at the end of the PV. So in 2 years, in 2 months from now, I will have a more definitive answer on how well we are doing. There are just some indication right now. For example, we astronomers speak in magnitudes when we look at an object. Right now, on the VIS instrument, we are at 2 decimal place from where we thought we were in terms of signal to noise. So it's really looking good. There is nothing that is really scary to the point of saying, oh, we cannot do the mission.
It works.
It works. Other questions? Don't be shy.
Thank you for the talk. And I'm wondering if you mentioned this kind of relationship with the United States. I'm wondering if you have another relationship with Russian, Indian, or Chinese space agencies, or are they investigating something similar about dark matter?
So we don't have we are not the consortium, the Euclid consortium doesn't have India, China, or Russian scientists. Also, for a very simple reason, the detectors that are in NISP are provided by the US, and with ITAR regulation, they would not be allowed to be passed in the hand of our Russian or Chinese colleagues. That's unfortunate, but that's the way.
To be more precise, the infrared detectors
Yes.
are sensitive things, because they are used to do spy satellite to observe the Earth, and therefore nobody wants to pass the knowledge of how an infrared detector is done to someone else.
But for Euclid is like that, but there are other missions in which there are collaborations with other countries. There is a collaboration EXTP, which is X-ray satellite.
In general, there are connections.
So there are collaborations with countries all over the world.
Indeed, and France, for example, is going to launch soon SVOM, which is a French-Chinese collaboration to look at gamma ray bursts.
If I can say, I think that there are less collaborations than what I would like to have.
Yes, I agree.
There are some, but in this particular period, for political reasons, Europe does not want to collaborate much with China, for example. And therefore, these kind of collaborations are a bit shrink.
Not to mention the collaborations which we had with Russia and now are somehow frozen.
I think that Europe, in this case, I mean, I'm expressing my personal feeling. It's not doing really the right thing. You should keep in mind that the only place in the world in which there is an active collaboration among US scientists and Russian scientists is the International Space Station. So I think that it's really important to have places in which science can act as something to put together people instead of splitting people. The International Space Station is one of probably the only example in this very moment of this kind of collaboration. And I personally think that this should be actually improved. Europe should probably play a better role in this. Anyway, other questions or yes?
Hello everyone, thank you for the talk. I would have a question for Eric and also other participants if they want to butt in. I would like to know what was it like doing PhD on Euclid, and what were the challenges you faced, and perhaps give some advice for all the other people here that are looking towards a PhD potentially.
Well, wow. No, well, actually, I didn't do my PhD in Euclid. I was on a project which was side to Euclid, but Euclid related. And I'm following right now a PhD student who is involved in Euclid stuff. Of course, from a certain point of view, it's probably one of the best things that could happen to you after when you graduate and you start your PhD, because of course it's a huge collaboration. There's a lot of stuff to do. There's a lot of science to do. And I mean, you don't get bored. I mean, there's really a lot to learn also. On the other end, as Bianca said, probably now that we launch, it's going to improve a lot. But at the beginning, it wasn't that easy because you don't publish, basically. And for how the system works, it's an issue because you risk to not publish. And usually we try to make our PhD students publish something related to Euclid, not official Euclid, blah, 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 all that kind of stuff. But of course, there's a lot of science to exploit during your PhD if you work in these collaborations. Probably, as it happened to me, the best thing to do is to put your foot within the collaboration, meaning starting to work with scientists in the collaboration, and keep your projects, at least during the PhD, kind of separated from the main flow of the Euclid.
No,
something like that.
I don't totally agree. I mean, it was like that for sure up to now. Now that the satellite is dead, now that the data are arriving, now it's a good time to make a PhD on Euclid. I wouldn't have given a PhD project 5 years ago, especially on the scientific side.
Yeah, well, now we are doing science, so we are going to publish as well.
Now
I agree. It's true.
It's better.
I mean, right now, if you start now your PhD on Euclid, you get to see the first data before the rest of the world sees it. You get to work on the data, and you have, and you will be part of the batch of papers that will accompany, go out with the first data release. It's the best time of to do a PhD in Euclid. It's really now, and there is a lot of work to do, and it's very easy to find a project within the collaboration that are PhD materials without any problem.
Other questions? Yes, here.
Hello. So my question is for Eric as well. Like, he is managing the technical aspects. So when the Euclid was launched, there was some technical difficulties with the velocity measurement. So, and it was handled well at that point. So are there any possibility in the future that we're gonna face some technical issues, and how do you plan to tackle them? Thank you.
Sure.
Well, for sure it can happen. I mean, the instrument is not perfect. I mean, it can fail, of course. We had issues. Hervé told us a couple of them. I mean, it happened. The point is, the whole system has a nominal, let's say, way of work and an emergency way of work. So the idea is to handle issues, if they happen, of course, by basically put all the people that really understand the instruments, so the people that built the instruments, so the people who twisted the screws of the instrument and know how that damn thing works really, and people like me, for instance, that knows how we handle the data, and put them together in a room for a couple of weeks. Basically, that's the way of of approaching this stuff, this kind of stuff. Because if you have an emergency, of course, you stop everything. You put the expert, let's call them the experts, the people who knows the instrument in a room, and they have
Lock
to,
the door.
you lock the door,
throw
throw the key,
away
and
the key.
they have to find a way to solve it. That's, but hopefully the worst is past. It's behind us.
I think that time is ended, so we have to close this event. I would like to really thank again all the speakers, Eric,
thank you,
Bianca, Hervé, Enzo, and Lorenzo. I think it was interesting, and I hope it was interesting for you. So thanks everybody for coming, and I hope that in 1 year we'll be here again to show exciting results from Euclid. Thanks a lot.